Okay, welcome back to this course on stereochemistry. During my last lecture, what we have discussed is the conformation analysis of acyclic systems, that means compounds which are not cyclic, which has got only carbon chain like this in a linear fashion. And then we have done the conformation analysis of N-butane. Then we have done the conformation analysis of systems which have got also this type of a 2 carbon system with different heteroatoms attached to the vicinal carbons, and we have done the conformation analysis. So, today we will start the cyclic system, the conformation analysis of cyclic system. Now, there is the first difference between the cyclic and the acyclic system is that cyclic systems do not have that much flexibility like the acyclic systems. In acyclic systems, the flexibility, that means the rotation is having a very free riding, and it is occurring much faster than in a cyclic system. Cyclic systems are much more rigid than the acyclic systems. Now, the cyclic system starts with a 3 carbon. Obviously, you need 3 atoms to form a cycle. So, it starts with a 3 carbon system called cyclopropane. So, if we have all these hydrogens, so this becomes cyclopropane. That is the first member of the cycloalkane series. Then the second member is the cyclobutane, and so like that the third member will be cyclopentane, and so on. So, you can increase the size of the cycle by adding more carbon atoms in the ring. Okay. So, cyclopropane, this is cyclobutane, this is cyclopentane. So, we will try to focus on our attention first to these 3 systems. Okay. Now, initially what was thought about these cyclic systems, that they are planar molecules, they are flat molecules, they are planar, and if it is planar, then what happens? There is a question of what is the angle then between this carbon carbon bonds between the 3 carbons. What are the bond angles then? If it is cycle, it is flat. If it is planar. Okay. Now, we know that different kinds of strain are there that can be present in a molecule, like the torsional strain, the steric strain, okay, the bond opposition strain. Those type of strains you have been introduced. Now, today we are going to introduce another kind of strain, which is called the angle strain. Okay. The angle strain is that whenever the bond angle cannot maintain the angle which is required for the kind of hybridization that the atom is having, and that demands an angle according to the type of hybridization. So, if the angle deviates from the angle that is demanded as per hybridization, then the molecule suffers from what is called an angle strain. I repeat again, the angle strain arises when the angle which is required as per the hybridization of the ring atom, it cannot be maintained, then the molecule will suffer from what is called an angle strain. Okay. Now, let us take this example, cyclopropane. Now, cyclopropane obviously is, as it is a 3 carbon system. So, it has to be planar, because 3 carbon system cannot be a non-planar molecule. So, the assumption that the people were having, people mean scientists in those days, it is I am talking about late 19th century, when there was a scientist, his name was Bayer. You know something about Bayer's strain, Bayer's rule, those are there. So, Bayer, he was the one who proposed that these molecules, cyclic molecules are all planar, and while adopting this planar conformation, they suffer from what is called this angle strain. So, in addition to the other kinds of strain, which is the torsional strain or steric strain, it also suffers from another strain, a new concept, which is the angle strain. Again I repeat, angle strain is the strain that is imposed because the proper valency angle as per hybridization cannot be maintained in the system. Okay. Cyclopropane, it is a 3 carbon system, it has to be planar. So, what Bayer said must be correct, that it has to be a planar, it is planar. Okay. You cannot get a non-planar system out of a non-planar cycle out of a 3 carbon system or a 3 points, that means a triangle has to be planar. Okay. Now, if it has to be a planar molecule, then what happens? The angle becomes 60 degree. If you think that this is a very rigid system like this, it is a mechanical system that only these are tied up by bonds. Okay. Now, the angle is 60. Now, what is the hybridization states of these carbons? They are sp3. So, the sp3 hybridization of carbon demands that the angle should be, it should be 109 degree, around 109.5 degrees, but it cannot maintain that because while making the cycle it is not possible. So, the angle is now 60 degree. Again I repeat, considering that this is a very mechanical system, that these are just connected by straight lines which are acting as bonds. Okay. So, now this molecule will suffer from angle strain because the normal valency angle cannot be maintained. So, what is the angle strain? Now, the definition of angle strain is that what is the normal valency, what is the normal valency angle or you can say what is the normal valency angle as required by hybridization minus the actual angle Now, this is interesting, this has to be divided by 2. So, what is the angle that is required as per hybridization? That is the normal valence angle, that is 109.5 degrees, but the angle is 60 degree as per this geometry of cyclopropane. So, the valency, the difference comes out to be 49.5. Okay. So, the angle strain is 49.5, but that is not the correct representation of angle strain. It has to be divided by 2. Why divided by 2? Because if you have the normal valency angle like this, 109 degree to 109.5 degrees, 109.5 degrees. So, in order to make cyclopropane, what you have to do? You have to bring this bond towards this carbon, and you have to bring this bond towards this carbon. So, ultimately this 49.5 degree deviation is evenly distributed between both the bonds. Okay. So, each bond is suffering an angle strain of half of this 49.5, because this you have to bring about what 24.75 degrees, and you bring this to 24.75 degrees, then you can combine these carbons with this carbon. This carbon you can connect with this carbon by lowering the bond angle, by moving this by 24.75 degrees. Okay. So, basically the angle strain, because it is shared between both the hands of the carbon, both the bonds of the carbon. So, you have to divide it by 2. So, that is the angle strain in case of cyclopropane. It is an enormous strain, and if you try to build up the model of cyclopropane. So, let us see, cyclopropane can be, this is what is propane. Okay, this is what is propane. Now, in order to just the propane is only one. So, it is propane. So, if you want to make cyclopropane out of the propane, then what you have to do? You have to combine these two bonds. You have to combine these two bonds, but you see there is lot of strain and bending that is associated with this. So, what happens to these bonds? Look at the bonds very carefully. If I place it here, let me see whether it comes in the camera, but it is not coming. So, better again lift it up. So, you see that the strain that is now involved in the molecule. The molecules are no longer linear. So, it has to be bent. We have to force these bonds to connect with each other and then make the cyclopropane. So, these bonds are suffering from this angle strain, and as I said, because you have to move both the bonds, so it is equally shared by both the bonds. That is why attached to the carbon, that is why you have to divide the angle strain, the deviation from the normal angle divided by 2, the magnitude of deviation divided by 2. So, this is how the story started. Okay. Bayer started calculating the angle strain, and he said that as the angle strain is more in cyclopropane. So, it is highly unstable compound, and if you make the cyclobutane now, if you consider cyclobutane, so this is cyclobutane, you see, you compare these two, you can see this, the amount of bending of the bonds is less in cyclobutane, the amount of bending in both the bonds. So, this is cyclopropane. So, you see I have forced almost the molecule is breaking apart, but in cyclobutane, you see in cyclobutane that type of strain is not present. It is still little bit bent, but it is less than the cyclopropane. Why is that? You can calculate the angle strain, and then this is the angle strain in cyclopropane. So, what happens? The angle strain in cyclobutane will be the angle strain. So, if I say AS is equal to 109.5 minus 90. Now, it is cyclobutane. So, these angles are 90, considering these are regular the square, okay, considering it as a square. So, that angles are all 90 degree. So, regular polygon. So, 109.5 minus 90 divided by 2. So, that comes out to be 19.5 by 2, and finally, you see it will be 9.75. So, 9.75 is the angle strain. So, earlier it was 24 in cyclopentane, the angle strain was 24.75. Okay. So, the angle strain is more in cyclopropane than in cyclobutane. So, this is more unstable than this, and this instability is due to what is called the angle strain. Sometimes it is actually referred to as Bayer's strain also. Bayer's strain means Bayer's angle strain. Okay. So, Bayer's strain is more in this system. So, this is less stable than cyclobutane. Okay. So, up to this point was very fine. Then if you take cyclopentane, you can calculate the angle strain again. And what will be the angle strain here? If it is a regular pentagon, then the angle will be 108 degree, and you see it is so close is very close to the angle that is required as per hybridization of the carbon, that is 109.5. So, the angle strain here is very little, you can calculate, that is angle strain will be only 1.5 divided by 2. So, 0.75. So, according to Bayer-Strain theory, the stability order will be cyclopentane should be more stable than cyclobutane, which in turn should be more stable than cyclopropane. Okay. This was fine, up to this point was fine, but the problem started when you increase the size of the ring beyond 5. Okay. So, what is the next homologue of cyclopentane is the cyclohexane. So, if you now write cyclohexane, I remove the carbons just the normal way, otherwise it will take more time if I write CH2s. So, this is your cyclohexane. So, now if cyclohexane is a flat molecule, is a planar molecule, it is a regular hexagon, then the angle becomes 120. So, the angle strain will be, now the angle strain will be 109.5 minus 120 divided by 2. So, it becomes a negative quantity now, because you are now increasing the angle beyond whatever is required as per valency. So, this will be now 9.5 divided by 2, but there will be a minus sign, okay, minus, and so that will be minus 4.75. So, the angle strain, the magnitude of angle strain, whether it is positive or negative, that is not the important issue. That important issue is how much you have deviated from the normal valency angle. Okay. So, you have deviated 4.75 here, the angle strain. In case of cyclopentane, it is only 0.75. So, according to Bayer's strain theory, cyclopentane should be more than cyclobutane, that is correct, that will be more than cyclopropane in terms of stability, but what about cyclohexane? So, as per Bayer's strain theory, cyclohexane should be less stable than cyclopentane. So, again I write, so these are the calculations I write, this is the, so now so we can say as per Bayer's strain theory, strain means the angle strain, cyclopentane should be more stable than cyclohexane, and if you continue to increase the number of carbon atoms, then cyclohexane should be more stable than cycloheptane. Okay. So, if you try to draw a graph about the stability of these systems, so if cyclopropane is here, then cyclobutane, then cyclopentane, then cyclohexane, then cycloheptane, cyclooctane. So, again it rises the angle strain, but in actual case that does not happen. So, up to this 3 to 5, whatever Bayer's strain theory is telling, this is followed. That means cyclopentane is more stable than cyclobutane, cyclobutane is more stable than cyclopropane. That was followed, and that can be explained in terms of the angle strain which was introduced by Bayer's, but then the theory falls apart if you increase the, when you increase the number of carbon atoms, and in fact ultimately it was found that amongst all the cyclic systems, the most stable system is cyclohexane. So, the actual is, this is wrong, what is correct is the reverse. Cyclohexane is more stable than cyclopentane, then comes the cyclobutane, and cyclobutane is more stable than cyclopropane. So, here we have a problem now. So, there must be something wrong with Bayer's strain theory. Okay? So, it is not dictated by angle strain. When the number of carbon atoms is increased, gets increased in a cyclic system. Okay. So, we will come back to Bayer's strain theory, but before that one might ask a question that how do you measure the stability of a compound? How are you measuring the stability of these systems, the cyclopropane versus cyclobutane, all these. So, a very good way to measure the stability, because that is a very valid question, how do you know which one is more stable, which one is less stable. Now, here again a very important concept that sometimes students get confused, that sometimes students feel that a less stable system is more reactive than a more stable system. That may not be true always, because reactivity depends, is a kinetic factor, is a kinetic issue. So, there may be a compound which is more stable than another compound, but it is more reactive. Okay. So, that may happen, because reactivity depends on the activation barrier of the process. So, if I say that cyclopropane is very unstable and it reacts with so many reagents, like cyclopropane reacts with hydrogen, you can get back the propane, the linear propane. If you add bromine, it adds bromine like a double bond is present. So, you will get 1,3-dibromopropane. But that does not really tell you that it is less stable than cyclobutane. Stability is a thermodynamic quantity and reactivity is a kinetic quantity. Okay. So, you must be very careful. So, if somebody asks that, show that cyclopropane is less stable than cyclobutane, and if you say that cyclopropane reacts with so many reagents, whereas cyclobutane does not, but that does not, that is not the correct answer, because that is a reactivity thing. Reactivity depends on the activation barrier. Okay. So, stability is the thermodynamic stability. So, how do you determine the order of stability of these cyclic systems? The best way is that if you burn these, if you burn any hydrocarbon, the product that you get is carbon dioxide and water. So, the end product is same. So, if your hydrocarbon lies at this energy level, suppose this axis is energy. So, if this is the energy level and if this is your hydrocarbon, so when you burn this hydrocarbon, so what you get is the end product carbon dioxide and water. Suppose the combined energy lies here. Okay. So, that is these are more stable. So, it is always an exothermic process. Okay. So, some heat is liberated from the hydrocarbon. Okay. So, if you take suppose cyclopropane, you burn it, so you will get carbon dioxide and water. Okay. And suppose this is delta H for cyclopropane, Cp, cyclopropane. Now, there are 3 carbon atoms here. So, in order to normalize these values in comparison with cyclobutane and cyclopentane, what we do? We calculate the heat of combustion that is there divided by 3, because there are 3 carbon atoms, 3 methylenes are there in cyclopropane. Okay. So, you divide it by 3 and see what is the value, and you do the same thing with cyclobutane. So, if you burn cyclobutane, you will again get carbon dioxide and water, and if this is this is that H, the delta H of cyclobutane. So, when you want to compare this versus that in terms of stability, so you compare delta H for cyclopropane divided by 3 and for cyclobutane delta H cyclobutane divided by 4. Because there are 4 carbon atoms, obviously more energy will be liberated, but for a particular methylene, per methylene, how much energy is liberated, for that you have to divide it by 4, you have to see number of methylenes here and you have to divide this by 3. Okay. So, that is now you can compare, because both are giving to the same product. So, this level is at the same, this energy level is at the same position irrespective of cyclobutane or cyclopropane. Only thing that if cyclopropane is here and cyclobutane is here, then there will be less energy that will be liberated when you burn cyclobutane. Again I repeat, this is I am comparing the energy that is liberated for each methylene in cyclobutane. So, if you compare this heat of combustion per methylene of cyclopropane versus cyclobutane versus cyclopentane versus cyclohexane. So, that will be a very good way to compare the stability of these systems. Okay. Another, some books write it this way, they compare the heat of combustion per methylene, and you can divide, you can subtract it from the, if you take the linear compound, a linear hydrocarbon compound, suppose N propane, and then you burn it. So, this is a linear compound, and you see how much heat is liberated per methylene in a linear compound. Suppose that value is say delta x. Okay. So, that is a constant value. So, you can actually see that what is the extra energy that a cyclopropane has, a cyclopropane methylene has over a methylene in a linear system. That difference also tells you about the instability of cyclopropane relative to a linear system. Okay. So, some books actually gave the values of these cyclic systems by not only saying the heat of combustion, but they do this difference. That means, you get the heat of combustion per methylene for the cyclic system minus the heat of combustion for the methylene in an acyclic system, and then these values are compared for different cycloalkanes. Okay. So, I will show you one slide that is there, which tells you about all these values, that what are the values of the different for different cyclic systems. See, this is I said 24.75. I think they took the correct, means I approximated 109.5 degrees. So, it is very close to 24.75. So, do not worry about the values here, they are very close. So, about I can say 25 degrees the angle strain in case of cyclopropane, and you see what is that value, that difference what I said, that the heat of combustion per methylene in a cyclic system minus the heat of combustion for a methylene in an acyclic system, you subtract those values and you see the values coming as, for cyclopropane it is 38.6, then 27.4, then 5.4. So, it is decreasing. That means, this is the least stable compared to the linear system. This is at least more stable than the cyclopropane, and this is here the value is the angle strain is only about 0.5, and then the heat of combustion, that difference is 5.4. In case of cyclohexane, this is interesting, the difference is 0. That means, the amount of heat that is liberated per methylene in a cyclohexane is exactly the same if you take the normal hexane. So, that difference is only 0. So, that immediately tells that this is the most stable system. Then as you increase the carbon chain, you see the carbon number of carbons in the cyclic system, then again it starts going up. It starts going up, but it never reaches these values. It remains more or less very close to between 5, 5.9, then it is again 5, 4.2. So, it really fluctuates. So, the graph will be something like this. The stability graph of cyclopropane, if cyclopropane is here, then comes cyclobutane, then comes cyclopentane, then comes cyclohexane, and then it just fluctuates like this. But this should be actually the bottom line. the minimum point. So, this is cyclohexane, this is your cyclopentane, this is your cyclobutane and this is the cyclopropane. Okay. So, this is the first thing that we have learned, that the strength theory holds good for cyclopropane, that is and then cyclobutane, it also as part of the strength theory, this is also unstable, but this is more stable than cyclopropane. And then cyclopentane is a 5-membered ring, where there is, you see, the bonds are almost linear, there is no bending of the bonds. So, that is not suffering from angle strain, there is very minimal angle strain. So, it is more stable than that. So, Bayer strain theory, these three are this following the lines what Bayer said, but then after this the whole theory falls apart. Cyclohexane is more stable than all these systems. Okay. Thank you. So, in the next one we will discuss the modern day concept of these cyclic systems, the conformation of cyclic systems.